Okay, let's start. Again, I put 4.2 and 4.3 together because they are both exponential functions, where 4.3 is a special case of 4.2. Now, what is exponential function? Let's start with the basic idea. Basic exponential functions have this look: fx equals to a to the x, where the a has to be positive. The a has to be positive and not 1. So if we imagine that on the number line, then the a has to be greater than 1. Oops. I'm sorry. The a has to be greater than 0. Why I keep on writing it? It has to be greater than 0 and cannot be 1. Okay, so it can be only from 0 to 1, not including 1, and 1 to infinity. That's what the base can be. I will explain later on why we only deal with a positive base and why the base cannot be 1. Let's say, for example, we deal with fx equals to 2 to the x. Now, let's do this first for now. Let's find some special values for this 2 to the x. Let's say I would like you to compute the value of the function if x equals to 0, 1, 2, -1, -2. Give me a second. It's quite sensitive. Okay, so when x equals to 0, what's the value? Equals to 1, equals to 2, equals to -1, equals to -2. What's the value of when you plug those x into the function? Like when x equals to 0, the y will be 2 to the 0, which is
1.
1. And then this is 2 to the 1 is 2. 2 squared is 4. 2 to the -1 is 1/2. 2 to the -2 is 1/4. Right? Now let me try to sketch that graph. Give me a second. I need my snipping tool. Now, if I plot these coordinates, let me use red color. 0, 1 is here, 0, 2 is here, 0, 4 is here, negative 1, 1/2 is here. Oops. Negative 1, 1/4 is here. Okay, in fact, if I go on further, when x equals to 3, the y is 8, right? So approximately, the graph looks like the following. If we keep on going further. Okay, now you'll see that if I go to the uh, uh, x equals to negative 3, then the y will be 1/8. We see this pattern that, I hope you can pay attention here. Notice that if at x equals to 0, the y is 1, right? Now, when x equals to 1, the y is 2. When x equals to, when x equals to 2, the y is 4. Notice that every time we move 1 unit to the right, we multiply the previous value by 2. We move 1 unit to the right, we multiply the previous value by 2. Do you see that? 1 multiplied by 2 gives you 2, multiplied by 2 gives you 4, multiplied by 2 gives you 8, and so on and so forth. Do you see that? Now, that's because the base is 2. It means every time we move 1 unit to the right, we multiply the previous value by 2. So 1 becomes 2, 2 becomes 4, 4 becomes 8, and 8 becomes 16, so on and so forth. Now, because when we move 1 unit to the right, we multiply by 2. When we move 1 unit to the right, we multiply by 2, multiply by 2, multiply by 2. Then the same idea, when I move to the left, I will divide by 2. Divide by 2. Divide by 2. You see what I mean? 1 divided by 2 becomes 1/2. When x equals to 0, you move 1 unit to the left, you get x equals to negative 1, right? Now then, the y will be divided by 2. 1 unit to the left again, you divide by 2 again, and so on and so forth. So every time we move to the left, we divide by 2, divide by 2, divide by 2, divide by 2. Okay, now, therefore you will see that while the domain of exponential function is all real number, we can plug in whatever x I want. However, the range will be from 0 to infinity, not including 0. In fact, the further we go to the left, the closer it will be to the x-axis, but never touch x-axis. Okay, as x going to negative infinity, the function f(x) will go to 0. Okay, but never touch 0. Okay, therefore we have a new terminology that y equals to 0 is the asymptote. Now let me go on. From here also, because the range does not include 0, then we know this basic function 2 to the x has no fx equals to 2 to the x has no x-intercept. Is it okay? Now, I have 3 coordinates here that I call important coordinates, such that every time you draw, I ask you to graph exponential function, you need to give me these 3 coordinates. Those are this guy here. Now, if we learn the term vertex in the past, when we did absolute value, when we did a square function, you know, we have vertex, right? Now you can see these 3 important coordinates here. When x equals to -1, x equals to 0, x equals to 1, in this case, as our quote-unquote important coordinates. Okay, now the reason I call this important coordinates because when we have exponential function, the bending of the curve is actually the steepest around these 3 numbers. Okay, which means the one to the right here, it is still growing exponentially, but it tends to be on the linear shape. Okay, it's quite linear, especially the one down here. It actually goes to the linear shape already. Okay, gets closer to y equals to 0 and eventually becomes linear, right? But the bending is actually the sharpest here around this area. Now, why do I say this? Because later on, when I ask you, for example, let's take a look on new question. Suppose, for example, I want you to graph y equals to, let's say, 3 to the x. Let's say x equals, y equals to 3 to the x. Then my y-intercept is 0, 1, right? Just imagine when the y-intercept, when x equals to 0, that's 0, 1. Okay, now the domain, because that's exponential function, the domain is all real numbers. The range will be 0 to infinity. Okay, and the asymptote will be y equals to 0. And the way I graph this, the y-intercept is 0, 1. Now, because the base is 3, then when I move 1 unit to the right, I multiply that 1 becomes 3. I move another 1 unit to the right, I multiply that 1, that 3 becomes 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9 here. And it becomes 1/3 here, 1/9, and so on and so forth. So the graph will be approximately like this. It's very, very close to the y-axis here. Now, those 3 important coordinates are this guy here, this guy, and this guy, and this guy. I always want you to give me these 3 coordinates. Now, why do I need that? Because imagine if I modified the question becomes, for example, example 2a, y equals to 3 to the x plus 2 minus, let's say, minus 4. Now, what will happen? Then the way we think is I start with 3 to the x which is the graph we have above. And what do we do with that? Somebody of you actually, someone of you make a lot of noise. Would you mind to mute? Thank you. Now we start with 3 to the x, which is the graph we have earlier, and then we move move 2 to the left, and 4 down. Okay, so then I will use these 3 coordinates to help me. Using this coordinate here, move 2 to the left and 4 down. 1, 2, 3, 4. This guy here, move to the left 2 units and move 4 down. This guy here, 2 to the left and 4 down. Okay, so now I have my new asymptote. My new asymptote will be here. This is my new asymptote. Okay, and my new graph will be approximately here. Now notice that my 3 important coordinates that I said earlier now move to this guy, and this guy. So I use these 3 yellow color coordinates here. Move these 3 coordinates to give me the framework for the new place of that 3 to the x plus 2 minus 4. Okay, now then, as you can see, that what's the domain of this new function? The domain will be, well, the original domain is already all real numbers, right? However you move it, then the domain will still be all real numbers. Now, the range, however, will change. Originally from 0 to infinity, but because we move it 4 units down, the range now becomes, you can see from the graph here, the blue graph, it will be from -4 to infinity. Okay, and then the asymptote will be y equals to -4. Okay, now one important thing to mention is, before we come back to graph, is the following, that one-to-one function, exponential function is one-to-one. Maybe I write it as a note here. Note, exponential function is one-to-one. In this case, because the function is increasing now. But the reason it is increasing is because the base is greater than 1 in these 2 examples. While, let's say, example 1, the base is 2. So every time we move to the right, we multiply by 2, multiply by 2, multiply by 2. While, for example 2, example 2 and example 2a, the base is 3, which means every time we move to the right, we multiply the previous value by 3. Okay, and it is still increasing function, therefore it is one-to-one. Now, what happens if our base is actually less than 1, but still positive? Let's say, for example, we have y equals to 1/2 to the x. Now, it means, give me a second. It means that, what is the y-intercept? The y-intercept is when x equals to 0, the y is 1, right? Still. For the basic function, you will see for the basic function y equals to a to the x, the y-intercept will be 0, 1. The domain is all real numbers. The range is from 0 to infinity. The asymptote is y equals to 0. Now, as you can see earlier, when the base is greater than 1, the function is increasing. You will see here, if the base is between 0 and 1, the function will be decreasing. Why? Because the base is less than 1. In this case, the base is 1/2. Means every time I move to the right 1 unit, I multiply the previous value by 1/2. I multiply the previous value by 1/2. By 1/2. By 1/2. And every time I move to the left instead, I divide by 1/2, which means multiplying by 2. Divide by 1/2, dividing by 1/2 is the same to multiply by the reciprocal 2. Right? Okay? So when I move to the left in this case, I divide by 1/2, which gives me 2. Divide by another 1/2, I give me 4. Divide by another 1/2, give me 8. So the graph for this 1/2 to the x is approximately as the following. You actually can see this as 2 to the -1 to the x, which is 2 to the -x, which can be obtained from example 1. Let me go to example 1. This is example 1, right? But you replace this x here by -x, replacing 2 to the x in the 2 to the x. You have 2 to the x. Now, when you replace x becomes -x, when you replace x becomes -x, we actually reflect with respect to y-axis. Okay, so originally it's supposed to look like this. This is 2 to the x if I draw it here. This is what 2 to the x looks like. Right? Now imagine if you reflect that with respect to the y-axis, then you get this 1/2 to the x. Well, anyway, you can just plot it the way I did earlier, like because the base is 1/2, then every time I move to the right, I move 1 unit down, I mean half unit, I multiply by 1/2 the previous value, 1/2 the previous value, 1/2 the previous value. Okay, or in this case, it happens to be something we can do reflection on the previous function we have. Okay, but the first method is still the one that you need to know. I can do this. Okay, so again, if the base is greater than 1, the function is increasing. If the base is positive but less than 1, the function will be decreasing. Okay, either way, because it's either increasing or increasing, then you will see fx equals to a to the x is a one-to-one function. Okay, and that property becomes an important property for us to solve some basic exponential function. Let's see, for example, so solving basic exponential functions. basic exponential equations. Let's say, for example, I pick number 2. I think that's the easiest one I can get for you. Number 2, we have 6 to the 7 minus x equals to 6 to the 2x plus 1. Now, notice that on the left-hand side, that's exponential function base 6. On the right-hand side, that's also exponential function base 6. Because they have the same base, then we can say 7 minus x equals to 2x plus 1. Now, the reason is exponential function with base 6, actually any exponential function, is a one-to-one function. Therefore, if they have the same base, then they must have the same exponent. That's what I did here. Okay, now therefore I can go on solving it. I get 6 equals to 3x, x equals to 2. Okay, so you can check, even though it's not necessary, you can check when x equals to 2. When x equals to 2, on the left-hand side, I get 6 to the 5th, and on the right-hand side, I also have 6 to the 5th. Is it right? Now, that's the easier one. Let's do a harder one, slightly harder one. What happens if the base look different, but it's changeable? Let me do number 4 first. Number 4, 9 to the x squared, 9 to the x squared equals to 3 to the 3x plus 2. Now notice that the bases are different. However, I can change this 9 into base 3. So I can write it as 3 squared to the x squared equals to 3 to the 3x plus 2. And then using properties of exponent, power rule, then I will get 3 to the 2x squared equals to 3 to the 3x plus 2. Now then, by one-to-oneness, I can say 2x squared equals to 3x plus 2. From there, we solve it further. Two x squared minus 3x minus 2 equals 0. I solve it by factoring. If not, then I use completing the square root formula. And from here we see that x equals to -1/2 and x equals to 2. Okay, that's for number 4. Let me ask you to try number 8. Number 8, we have 27 to the x minus 1 equals to 9 to the 2x minus 3. Now, what you need to do is to change the bases, even though they are not common bases. Okay, but each 27 and 9 are actually base what?
3.
Base 3, that's right. So I can rewrite 27 to 3 cubed and 9 to 3 squared. Now, let me ask you to finish that. What do you get?
X equals 3.
X equals 3. I think that's right, but let me check. So by one-to-oneness, I get 3x minus 3 equals to 4x minus 6. 3x to the right becomes 4x minus 3x, that's x. Negative 3 plus 6, that's 3. That's right. So x equals to 3. Okay, let's go back to graphing. This time, then, we can ask even more important questions. Let's say I have let fx equals to, I usually use base 2 because we can see more details there compared to base 3 or higher base. Let's say I have 2 to the x plus 2 and then minus, let's say minus 8, why not? No, don't use minus 8, make it minus 4. Make it minus 4. Now then, the first question, easiest one, what is the domain?
All real numbers.
That's all real numbers. Now, as for the range, notice that originally the range is 0 to infinity, right? And then we move 2 units to the left. Moving to the left or to the right will not change the range for any function. For any functions, moving it to the left or to the right will not change the range. However, the one that changed the range is when we move it 4 units down. So what is the new range now?
Negative 4 to infinity.
Negative 4 to positive infinity. Okay, so for y equals to 2 to the x, the range is from 0 to infinity. Moving it 4 units down, now the range becomes negative 4 to infinity. How about the asymptote?
Y equals negative 4.
Y equals to negative 4, good. How about the y-intercept?
Negative 2.
Are you sure?
Negative 2, negative 3.
Is it
No.
right? Well, let's see. What is f0? F0 will be 2 squared minus 4, right? What's that?
Oh, the y-intercept. So it would be 0.
That's 0. So the y-intercept will be 0, 0.
Yeah, okay.
Okay. So the y-intercept is 0, 0. How about the x-intercept? The x-intercept, so I set the y equals 0, 2 to the x plus 2 minus 4. And then 4 equals to 2 to the x plus 2. So 2 squared equals to 2 to the x plus 2. Therefore, 2 equals x plus 2. X equals to 0. So the x-intercept is also 0, 0. Which actually something we already have because we know the y-intercept is 0, 0. Which happens to be the x-intercept, right? Okay, and because the function is 1 to 1, once the y-intercept is x-intercept, there won't be other x-intercepts. Now, the problem is, how do we graph this better? Then we will use the coordinates that we have before, those 3 important coordinates. The one, maybe I use this color better. The one that we have here, do you see this? Here, here, and here. For 2 to the x. So Originally, for example, this guy here, do you see my blue color? 0, 1, move 2 units to the left, 4 units down. Now it's here. Now it's here. And then 1, 2, 1, 2, 2 units to the left, 4 units down. Now it's here. Negative 1, 1 half, originally here, 2 units to the left, 4 units down. Now it's here. In fact, I know that the horizontal asymptote is y equals to negative 4. Now, if I continue with the graph, then it will be 4, actually 8. So the graph will be approximately like this. And you see how I use those 3 important coordinates we have earlier to help me graphing this exponential function. Those 3 important coordinates now becomes here.
Thomas, do you want us to label those 3 coordinates on an exam?
No need to label it, but I need you to kind of like bubble it with this, like this here. You know,
Right,
you bubble
okay.
it a bit thicker. You know.
Right.
Yeah.
Okay.
Okay.
Thank you.
The reason I don't need you to label it, because imagine if we label it, it gets too crowded.
Yeah.
You know, right? Negative 1, negative 2, and this is negative 2, negative 3. It's too crowded, so no need. No need.
Okay. Thank you.
But good question. Good question. Yeah, I need you to just at least you make it bold, the coordinate kind of thicker. Okay, you don't need to highlight it like with green color like what I did here. No need, but make it thicker. That's good enough. Okay. You see that in my old test, I always ask a graphing problem. So please be strong on graphing problem, even though I have to say that I really consider graphing this exponential function is quite a bonus for you, because you already see this, supposed to already seen this in intermediate algebra, okay? But because the concept of graphing exponential function is important, that's why I repeat it again here. Now, with this said, then I need you to help me imagining the following. Call this a side note, but important side note. Suppose I have fx equals to a to the x. Now, when the a is greater than 1, then as x going to infinity, what's the function be? If the base is greater than 1, it means every time we move to the right, it will multiply by something greater than 1, right? Like this 2 to the x, where's that? This 2 to the x and 3 to the x, the red color here. The further we go to the right, what happened to the graph? It will explode to infinity. While when x goes to negative infinity, the function will get very close to...
Gets very close to the horizontal asymptote.
Which is?
0.
That's right. Okay, now that's the first part. Now, when the base is between 0 to 1, then what is the far right behavior? When you go to the very far to the right, the function will be closer to, now you can imagine this function now. Right? This is when the base is between 0 to 1, right? Okay, so when I go very far to the right, the value of the function will be getting closer to 0. And when I go very far to the left, it instead goes to infinity. Okay, that's a side note. The first side note, I should say, very important one. The second side note, which is not that important but nice to discuss, is actually a big question. Why the A cannot be 1? It has to be positive, but why all of a sudden you discriminate against this 1, a number that we love so much? Because of the following. Let's see. Let y equals to 1 to the x. Now, what is 1 to the x?
1.
That's equals to 1 for every x, right?
Yeah.
That's for every x. So when we graph that, this is actually just a constant function. Now, why do we don't deal with constant function? That's nothing fun there. Okay, nothing fun there. And actually, of course, I'm partially joking when I say nothing fun there. Nothing fun with constant function, especially y equals to 1, that's horizontal line. But another main reason why we don't want to call y equals to 1 to the x as a basic exponential function, because notice that, let me graph that first. Let me graph that first. Let's say this is my my coordinate system. Let's say this is my coordinate system. Then y equals to 1 is basically this line here. Okay. The y-intercept still 0, 1, the way our previous exponential function looked like. The y-intercept is 0, 1, right? The y-intercept is 0, 1. It doesn't have x-intercept, but the difference is actually at the, of course, the range. The range is not 0 to infinity anymore. What is the range here?
One to infinity.
Is it 1 to infinity? The range is actually only 1, which is 1.
Oh.
Right? Whatever x you plug in, the output will be 1. Right? Okay, so the range already changed. If the base is different from 1, however slightly different it is, the range suddenly becomes from 0 to infinity. But once the base equals to 1, it suddenly becomes a constant function. Okay? And another reason why we don't want to categorize this as exponential function, because the fact that it is not increasing, not decreasing. And therefore, it's not a one-to-one function anymore. Okay? In other words, we don't consider 1 to the x as a basic exponential function, because the properties of the exponential functions in general suddenly not apply in this case. Does it make sense? It's not increasing, it's not decreasing, it's not one-to-one function. The asymptote supposed to be y equals to 0. All of a sudden, it is not 0. Suddenly becomes y equals to 1, right? Okay, so that's the reason we don't consider base 1 as exponential function. Now, so why do we need to avoid the base to be negative? Why a cannot be, the base can't be negative? Okay, what's the reason? The reason has something to do with ambiguity. That's at least one of the big reasons. Now, let's take a look, for example, let fx equals to, let's say, negative 2 to the x. Now, notice that by our definition, this is not an exponential function. Not an exponential function, at least for our level. It's not an exponential function because the base is negative. Okay, now the question is, why don't we want to call this an exponential function? Because of the ambiguity. When x equals to 1 is easy. When x is an integer, it's easy. Let's say f equals to 0, then negative 2 to the 0 is 1, right? F1 is negative 2 to the 1 is negative 2. Is it right? Okay. But we have issue with fractions. What is f1/2, for example? That's negative 2 to the power of 1/2, right? Which is square root of negative 2, which is not a real number. Are you with me? Nobody say anything. Okay, fine.
Yes.
Yeah. So you see that something quite strange, that exponential function is supposed to be increasing, therefore implicitly it is continuous. But when we change the base to 1/2, I mean negative 2, all of a sudden you see that the y-intercept is 0, 1. When x equals to 1, that's negative 2. Yet when x equals to 1/2, nothing in there. It's not continuous, right? Okay, that's one reason. So we run out of continuity. Another reason, which is actually the better reason, is because of the following. Imagine if I rewrite this 1/2 as, imagine if I rewrite that 1/2 as 2/4. Now 1/2 and 2/4 are the same value, right?
Yes.
So the output supposed to be the same. Strangely, that's not the case here. You see that if I have negative 2 to the power of 2/4, one way to look at this is negative 2 being squared, and then you do the 4th root. Right? The 4th root of negative 2 squared. Now that's the 4th root of positive 4. Now, even though this is not a rational number, but it is still a real number. Now, so what's wrong with this? What's kind of inconsistent here? Notice that 1/2 is equals to 2/4, yet when I plug into the function, they're supposed to be the same. They're supposed to be the same, but it turns out that this is not a real number, yet this one is a real number. It's inconsistent. Do you see that? Okay, now because of this ambiguity for this situation here, then we don't talk about negative base until you get very, very far into math. In fact, as I remember, the first time I learned this is in complex analysis. It's your 400 level in math major or even master's program. Okay, but for now we don't talk about this because of this ambiguity, confusing. Don't know what happened. Let's talk about that later. Let's talk about this later. Okay, when? At least 3 years later. Basically, that's the way I say that we won't discuss that in this class. Okay, you may see this somewhere in future. Okay, I hope this way I give you the argument why then we insist the base has to be, we insist that the base has to be positive and cannot be 1. It cannot be 1 because when it is 1, suddenly it behaves differently. When the base equals to 1, suddenly the function behaves differently compared to when the base is greater than 1 or between 0 to 1. Okay, now when the base is negative, we have problem with ambiguity and continuity. Okay, yeah. So that's why the base has to be in this yellow interval here, yellow color interval. Now let's go back there. So we are done with the major part of this section. Let's do some more problems. In fact, I'm interested in some word problems later on. But let's do it later. Let's do more graphing problem. Let's say number 30. Oh, you know what? Hold on. Before I do number 30, number 24. Number 24. Fx equals to 2 to the negative absolute x. The question is sketch the graph. Notice that even though this looks like exponential function, it is not a basic exponential function. It is still exponential function, but it's not basic one. Why? Because it doesn't look like a to the x. You see, it's not x on the exponent in this case. It's not, right? Okay, but then how do I graph that here? It's not basic exponential function, Thomas, but how do we graph that? Then we break it up. We know that when x is positive, what happened to absolute x? Absolute x is x when x is 0 or positive, yet equals to negative x when x is negative. Now, using this idea, I plug that in here. So, when x is 0 or positive, the function is 2 to the negative x, right? When x is 0 or positive, absolute of x equals to x. Absolute of x is equal to x. While when absolute of x is negative, when x is negative, then absolute of x is negative x. So when I replace that here, it becomes 2 to the negative of negative x, which is 2 to the x. So what happened then here, we have a piecewise defined function. Okay, now how do we graph that? Let's see. To the right of x equals 0, or to the right of that, we deal with 2 to the negative x. So it looks like this. Here, here, here. It's supposed to be 2 to the negative x. Now this is 2 to the negative x. This is 2 to the negative x. Okay. However, we only take the positive branch. So I will erase everything on the negative branch. Okay. This is 2 to the negative x for x greater equals to 0. While on the negative branch, I use 2 to the x. I use 2 to the x. 2 to the x looks like this. Okay, but because I only need the positive, the negative branch, I will erase the the positive part. So the graph of the function actually looks like this. This is for this part here is 2 to the x for x negative. Okay, now as you can see, the graph on the right hand side and the left hand side, it's symmetric with respect to the to the y-axis, and the maximum value is positive 1. So if I have a follow-up question here, you take a look at the graph, then what is the domain?
Is it still all real numbers?
That's right, it's still all real numbers. How about the range?
Zero to 1?
That's
Zero.
correct.
No.
Yeah, that's right, 0 to 1. You're right. Okay. Not including 0, do we include 1?
No.
Do we include 1?
Yes. Yes.
Yes. Okay, now how about the asymptote?
0.
Almost right.
Y equals to 0.
Y equals to 0. Now, this time the asymptote is actually both ways, going very far to the right and very far to the left, right? In other words, I think to be more precise, the graph going to y equals to 0 on the far left and also far right. In our previous exponential functions, the basic exponential function, the graph goes to the asymptote only at one side, like in this case, only on the left-hand side, right? And then the one here, it goes to the asymptote only on the right-hand side, okay? But this, the one we have before, I mean, the most recent one here, the asymptote actually goes both ways, okay? Now, let's go a bit further. I think I want to do 2 more problems from here. Let's take a look on, for example, number 32. The question is, find an exponential function of the form fx equals to dax or fx equals to bax plus c. Now, take a look on number 32. Take a look on number 32. What do we see in number 32 from the graph? Maybe the asymptote first. What's the asymptote?
Y equals 1.
Y equals to 1. Okay, now once we know the asymptote is y equals to 1, we actually know something there right away. Let me give you a hint. We go back to our previous example. This one here. What's the asymptote?
Y equals to -4.
Now look at the function.
So there's no trailing constant then. There's just a base with the exponent.
That's right. Okay, so once we have asymptote different from 0, different from y equals to 0, that will be the constant part. Do you see that?
Mm-hmm.
Okay, let's see another one here. Example 2a. The asymptote happens to be y equals to -4 also. And that's -4 is the constant part. You see that? Okay. So using that idea, if I go back to our question, then what do we know? Once what we know from the function, once we know the asymptote is y equals to 1. Do we know the b or a or c?
C.
The c. Okay. So now I update this to be fx equals to b times a to the x plus 1. Now we have two coordinates on that graph. We have two coordinates on that graph, 0, 5 and 1, 7. So f0 is b times a to the 0 plus 1 equals to 5. Now, what is a to the 0?
1.
1. So I can just call that 1. Basically, it means b plus 1 equals to 5. So what will b be?
4.
4. Now, let's update our function then. So fx at this point is 4 times a to the x plus 1. Now, using that, f1 equals to 7. So 4 times a to the 1 plus 1 equals to 7. Now, what is a to the 1?
A.
That's a. So 4a plus 1 equals to 7. 4a equals to 6. Then a equals to 3/2.
3/2.
Or 1.5, right? 6 over 4, 3 over 2, 1.5. So our final function, we already get all ABC. So our fx now is 4 times 3 over 2 to the power of x plus 1. That's the function. Okay. I know we all kind of like get so fed up with the talk about COVID, the virus, right? And that's why we are here now. But to tell you the truth, which is a bad truth, a sad truth, is that the way a virus actually spread follows very closely exponential function. And according to some people's, some data, so some people using the data that are available, we found out that in New York, let me write it underneath. In New York, couple days ago, especially in New York City, they actually follows this following exponential function, b times 1.2 to the x. Basically, each day they add 20% of the number of people confirmed positive from the previous day. Now, this one, you don't need to write this down, though. I just try to relate what we learned right now to what actually happened right now too, okay? What happened with LA? LA until last week, LA County, until last week, it was 1.08 to the x. Okay, now the highest spread that is known happens in Italy. There was one time the contagious rate was to the point of 1.23x, which means if each day they add 23% to the number of people confirmed positive from the previous day, then the next day they expect another 23% increase from the current day, from today. So that's why this is how we kind of predict that, for example, in the case of New York, then we all, the government there, and of course us too, so afraid that, you know what, if it keeps on going like this, then let's say in 1 week, we don't have enough capacity to hold all these patients. That's why then they ask one US ship, I think US Comfort or US Mercy to be there to help to take care of the patients, even though it's still not enough if it goes on for 2 weeks. Okay, that's how we do the prediction. According to the news I read yesterday, I don't really watch news, but I read news. In LA, this is already going down a bit less right now. It's not 8% increase anymore, but it's less than that.
Oh, that's good.
Of course, that's good, you know, but I hope that's not temporary. You know, sometimes we get good numbers and then we kind of slack off. You see what I mean?
Yes.
Right? So please tell your friends, tell everybody in your family, in your household, please. It's getting better. It means we are doing the right thing right now. Okay. But we need to keep that for at least another 2 weeks.
Okay.
Yeah, our goal is actually such that there's no more growth. Unfortunately, the numbers that we see on what's that word index? So I think Wordo index. I don't remember. One website that actually put all the numbers there. The number of they only report more detail on the number of people confirmed positive. Okay, they do report about the number of people die or the number of people recovered, but everybody's eye is actually on the first column. I think, let me show you what I'm referring to. Give me a second. Oh, word or meter? You see this? Not the hand sanitizer. No, don't worry about it. Oh, I mean, that's what everybody kind of like try to chase. Let's see the number of the situation here. See the total cases? It's kind of following the exponential function, right? The death also. Now, of course, worldwide, it's still following exponential growth, okay? But if we look at USA, I think USA is still in general still going through the exponential phase. But what I know, for example, California, it's already not. It's already going through the exponential phase. So we are still increasing. We still have more people, right? Yesterday, from yesterday to today, we have 203 more people. But compared to yesterday, it's less already. Do you see that?
Oh, yes.
Okay, so it seems like hopefully this is the situation that we already go through that exponential phase. And notice that how long have we been how long have we been out of range? How long have we been sheltering? Do you realize that?
It's the third or the fourth week.
Yeah, this is
Yes.
this is the third of the fourth week. That's true, but that's for SMC and colleges,
Yes.
right?
But other
Okay.
people's barely
Yeah.
like 2 weeks, right? Some people's.
So the order of sheltering actually happens approximately 2 weeks ago, as I remember.
Yes.
Okay. Now after 2 weeks, we see the numbers start going down. I mean, we still have more people contracted, right? But it's less than what we have before. Look at New York. Look at New York. New York, 7,000. Yesterday is higher. Right? The new cases. Look at the new cases. Right? Now, of course, the total cases is always accumulative. So it's always increasing. Wait, hold on. Yeah. Yeah. So yesterday was 123,000. Today, the total cases is 130,000. But yesterday, they gained 8,000 people confirmed positive in that one day.
Wow.
Between yesterday and today, only 7,000 people. Of course, 7,000 people, don't get me wrong, it's still a lot. It's still a lot. But at least seems like we are getting better.
Well, California did improve a lot.
If you think about it, that's true. Yeah, if you think about it, that's true. Right?
So it's over 1,000.
Yeah, yesterday the increase, so from Saturday to Sunday, the increase was 1,300, right? But from yesterday to today, only 203. But of course, this is not the end of the day yet, so this may increase.
Oh,
Now, the one that I heard already start into the what we call exponential phase. You know, remember what I called exponential phase? It's when the exponent, the x positive. If I go back to our exponential functions.
And the value of x grows greater than 1.
That's right. Yeah. So what we call exponential phase is this area here. This area. This is the exponential phase. Like it's just exploding. You see? Now, it seems like California in general already going down. But of course, California consists of a lot of counties, a lot of cities, right? Okay, so we should not be too happy. At least, I mean, that's a good improvement, you know, in general. But we still need to pay attention to details, and everybody. The way I see is this: I know a lot of people still going out. They have their own reason. Of course, I would tell them try not to go out, but some people need to make a living. Okay, imagine in Indonesia, it's a lot worse. A lot more poor people there, right? So a lot of them now we have more hunger there because they have less access to food. So please don't get mad if some people have to go out. Okay, but the best we can tell them is like, please limit it, because in this case we are all together, you know. Okay, now the thing is, Louisiana, I heard, and Pennsylvania is starting their exponential phase. Let's see, Louisiana yesterday was 514. Today they have 3 times more. You see?
Mm-hmm.
Okay, which in my opinion is quite scary, right? Now, in couple days later on, you will see the number of new deaths they have will be increasing, which is usually being delayed by around 1 week to 2 weeks. Hopefully not. Hopefully not. You know, that's what our medicine. So from the new cases to the new deaths, those are actually in the hospital. Okay, we as the public should be responsible on the new cases. You see what I mean?
Yes.
Right? So don't just say, you know what, those people in the hospitals work. You know, we have to work together. Okay, people in the hospital supposed to be the last line of defense. We are the first line of defense. Oh, I talked too much about this COVID. I'm sorry. You know, to put you more into perspective. That's the reason I actually go for this. Let's go back to our lesson. I mean, sometimes talking about COVID is a bad news, but the reason I bring it up right now is because it's actually starting. We start to see the good news, and it's everybody's work. It's not one people's work. We need to give credit to our government, though. Okay, yeah. I mean, you like it or not.
Yes.
Yeah, and I would like to say that I give credit to our California government. Our governor. Okay, yeah, some people say, well, if he could have done it a lot earlier, it would be better. Yeah, if everybody knew what happened at that time, right? If everybody knew what happened in the future, then we all live in the future, not current. One more question before we take a break. The word problems. The word problems, let's say we do number 38. I like this question. Number 38. A drug is eliminated from the body through urine. Suppose that for an initial dose of 10 milligrams, the amount AT in the body T hours later is given by AT equals to 10 times 0.8 to the T. Now, you will always see that this 10 here is always the initial value. Why? Because when T equals to 0, you get only 10. Is it right? Now, second, notice that the base is 0.8, which means each hour only 0.8 of the previous hour's amount of the previous hour left. So let's say for example, just to give us some feeling, let's say for example, now I have 10, then 1 hour later, how much left? 0.8 of this. 10 times 0.8, that's 8. 2 hours later from now, that's 10 times 0.8 squared, which is 6.4, which is 0.8 times 8. Okay, so if I rephrase my question without giving you this equation here, without giving you this equation, I can say it this way: initial amount is 10 milligrams, and each hour the urine will release 20%. Can you follow my line of thought? Because in the next 1 hour, I keep 0.8 of that. I keep 80%, which means I lose 20%. Right? Okay? So later on, if we have this wording, then you know this is your equation. This is your function. Now, let's go back. They are nice enough, they tell us the function. Okay, part A, estimate the amount of the drug in the body 8 hours after the initial dose. So 8 hours after the initial dose means T equals to 8. That's 10 times 0.8 to the 8. Now use your calculator. 0.8 to the power of 8 multiplied by 10. I get 1.67772 milligrams left. Now, when you use your calculator, you may wonder, Thomas, how do I do this exponent 8? If you use scientific calculator, this is what you punch. You punch 10 first, okay, and then 0.8 to the power of 8. Now the exponent, you use this button.
Bless you.
Bless you.
Thank you. That's called coughing. That's not coughing. Okay, so for the exponent, we use this this notation, this button on your calculator. Now that's for part A. Part B, what percentage of the drug still in the body is eliminated at each hour? So each hour we retain 80%, which means we release 20%. So I implicitly already answered that earlier. Everybody with me?
Yes.
Okay. Now, the reason I pick up this question is because the following. Now, I believe this question is hypothetical. I believe this question is hypothetical, but it is actually quite following the reality that if you take some medicine, then the amount of that medicine stay in our body will be some initial value times a to the x, where the a, of course, should be from 0 to 1. The amount of the medicine, the the amount of the medicine inside our body will be getting less and less. Now, suppose the A is between 0 to 1, then you know that as x goes to infinity, what happened to this AT? Actually, I should say as t goes to infinity. The base is between 0 to 1. So the function will go to?
Infinity.
No.
Hold on.
Imagine if I have 0.8 to the x or to the t.
Oh, 0.
Goes to 0, that's right. So
Sorry,
also,
I forgot it was between 0 and 1.
that's right, yeah. Now, so here's the thing though. So we know it will be decreasing, right? We know it will be decreasing. Okay? Now, imagine how a medicine actually works in our body. Okay, so if you take a medicine and our body will react to that, let's say a painkiller, right? Our body will react to that as long as the amount of medicine in our body is more than what? Okay, so after a certain time, after 4 hours, for example, then our Advil or our Tylenol or our NyQuil doesn't work anymore because the concentration of that medicine in our body is already less than what our body be sensitive toward. Okay, so if the amount of that medicine in our body is already less than that, then we start feeling the pain again, okay, or we start our allergy again, okay. On the other hand, and the one I want to share with you even more is what happens if you take some drug, not medicine. Let's say, instead of medicine, we'll call that alcohol. After all, it starts with capital A, right? So imagine if you take alcohol, right? Okay, you get some booze. And once you have some alcohol, some vodka, for example, you should not drive. You need to wait. Until when? Until the amount of alcohol in your blood is actually less than certain value. Is it right? Okay. Now, everybody, do you hear me?
Yes.
Yeah.
Now, how do you reduce the amount of alcohol in your body?
Eating
Close enough.
or drinking more water.
Why drinking?
To decrease the level of alcohol concentration in comparison with other fluids in your body.
That's one. That's actually the first reason. And the second reason, so that?
Filter it out through your kidneys.
And?
Discharge it through your urine.
That's correct. So one of the main reasons we drink is actually to reduce the I'm not talking about like if you already drink alcohol, you cannot drive and therefore you drink more alcohol. No. If you want to reduce the amount of alcohol in your blood, what you do is you drink more water. Okay, or some people say some black tea, like very dark, kind of like very concentrated tea. Even though in my opinion, if you don't plan to sleep, we prefer to let you drink coffee, because coffee has the diuretic effect that makes you pee. What you don't want to happen, you drink a lot of water, okay, but the water is not coming out from your body. You see what I mean? So the alcohol is still in your blood, right? What you want is like you drink water and dilute that in your body and you pee some of them out. Okay, once you pee some of them out, you can drink more to dilute that even further. That's the idea, right? Okay. What happens if you have some crack, marijuana. Hey, we are using some science to see what actually happened. See, when I went to Marine, the drill instructor said this: whoever used marijuana in the past, in the last 4 years, you better let them know right away. Okay, and why 4 years? Because if you look at this exponential function, okay, the amount will never be zero in your body. Do you notice that?
Yes.
Right? Okay, that's only when t goes to infinity, the amount will be zero, right? That's if we live forever. So you measure the amount of marijuana in my blood like 1,000 years later, then I don't think you don't find anything anymore. You won't even find me, okay? But if it is only in 4 years, there is big chance that, let's say 1 year, okay? There's big chance that what you took last year, it still show up in your blood test today,
Wow.
okay? Now you know how bad it is when you take illegal drug, okay? You know, I mean, I think I should say it correctly. If you take a drug illegally that not prescribed to you, it stays in your body. It stays in your blood for a long time. Okay, so if you have to take such medicine for certain reason, then I really suggest you to do it under doctor supervision. Okay, don't do it on your own. Okay, because it stays in your blood for too long. Now it's already 11:03. Let me give you a break. We come back at 11:15. Okay.
Okay.
Okay. See you later. Okay. So I use the function again. At number 34. At equals to 10 times 0.8 to the t. Half-life or half-time. It's the time it takes to have the amount. Half of the initial amount. So if the initial amount is 10, then what is the half amount?
5.
That's 5. Now then the question is, what is the time such that 5 equals to 10 times 0.8 to the t? Are you with me? What is the time such that after that time only half left? You will see if I divide by 10, I need to divide by 10 first, right? That's 0.5 equals to 0.8 to the t. Okay, so later on we will learn to solve for t. Okay, later we will learn to solve for t. Okay, but for those who already took this class before or remember something from your algebra 2, this t is actually log base 0.8 of 0.5. Okay, now we will save this for now. We will come back to this maybe on Wednesday when we talk more about logarithm. Okay. Another thing from this 4.2 is how to apply this to money. Compound interest formula. Compound interest formula. You can see this on page 267, that the amount of at time t equals to the principal times 1 plus r over n to the power of nt. where the R is the annual rate. The N is number of periods annually. And T is number of years. Now, this formula is in the book. Okay. Usually, I don't ask this type of question in my test, but I'm planning that this time I will give you this question in the test. Do you need to memorize the formula? It's supposed to be yes. But to be honest with you, with the way I give my test, I don't even know if you open book, right? Everybody okay with that? Do you realize what you can do? Yeah. Yeah. Okay, so don't worry. If I give you this kind of question in the test, I will give you the formula also at the same time. Okay, so even if you can open your book, you don't need to open your book. Okay, let's learn how to use this formula. Now, let's say, for example, we use this formula a lot later on when you start working and start either investing or, to be more precise, saving. Let's say, for example, I deposit the principal to be, let's say, 20,000. So you have $20,000. You want to save this money for, let's say, 4 years. And then you save it into an account that they compound it every month, compounded monthly. So they take the interest every month. Then how many periods in 1 year?
12.
12. Now suppose the annual interest rate is 1.2%. Then what is the periodical rate? Per month, the interest will be 0.001 per month. Okay, notice that I changed that to decimal. I don't play with the percentage, right? Okay, now then the question is find the amount of money in the account at the end of the 4th year. At the end of the 4th year. Then the work will be, okay, then A4 equals to 20,000 times 1 plus, what is my periodical rate? My periodical rate?
0.001.
0.001 to the power of how many periods in total?
12.
12.
That's the number of periods in 1 year. In 4 years, then how many periods?
Oh, okay.
48.
48. Okay, so you see that this NT here, actually the total number of periods, and this R over N is the periodical rate. Okay, so this will be 20,000 times 1.001 to the power of 48. Now, let me ask you to use your calculator to compute this. We will only do one example from here, but I need to make sure you know how to use your calculator to compute this. What you get?
20,982
20,982.
with
How many
90
cents? 91 cents.
Yeah, 91.
Yeah, we round it to the nearest cent, right? Okay. Now, I think it's because the interest rate is so low, it's 1.2%, such that in 4 years, we only earn $982. Once you go to business major, I hope some of you are going to business major or econ major, and you will learn why the interest rate, they make the interest rate to be lower. Would you like the interest rate to be low or high?
Low.
You want interest rate to be
Higher, depends on the,
depends on what you do, right?
yes.
If we are saving, I deposit my money to the bank, I want the interest rate to
One
be
the
high,
higher.
right? Okay, but if I am the one borrowing money, I want the interest rate to be low,
Yes.
right? Okay, so interest rate is kind of like a hard topic to talk in the governmental policy, because if the interest rate is too high, then we, especially you youngsters, because we tend to borrow money during this phase in our life for our student loan, let's say, or when we buy a car, or hopefully one day you buy a house, you know. But we don't buy a house. We usually don't buy a house with like with cash, right? Like the house is 400,000 and I just dump 400,000 to that person. Usually no, we usually pay that in using mortgage, right? But if we we borrow money, we prefer the interest rate to be low, okay? So, but if the interest rate is to be too low, then people who already retired, whose money, their income actually depends heavily on the interest rate, okay? Then they may have harder time. So it's not easy to be your government, okay? Interest rate to be too high, that's bad for some people. To be too low, also not bad, not good for other people, okay? Even if the interest rate is at the right place, at the right number, some people still complain, you know. So this is how we use interest. Exponential functions. One of the big application is into compound interest. There are actually a lot more we can say here, but I will just leave it there. Do you need to memorize the formula? It would be nice if you know how to use it and how to use your calculator, but I will give you this formula during the test. Now, what happened with 4.3, by the way? In section 4.3, they deal with natural exponential function. Natural exponential function. Where the base y equals to ax that we talked about before, we change the the base becomes e. Now this e is, they call that a natural number 2.71828 blah, blah, blah. It is an irrational number, okay? Because it is an irrational number, we usually just write it using letter E. Now that's what we talk about in this section. That's why earlier I said that 4.3 is a special case of 4.2, in which the base, which was either 0 to 1 or greater than 1, cannot be 1, right? Now we replace that a, the base becomes 2.7 something. Now because the base is greater than 1, then we know this function is increasing. Okay, now this e is a special number in math. The reason is because of what we learned earlier in the amount of money we have after depositing. Let's say we have something like this. Let's say we have something like this. And n is the number of periods annually. And in our previous example, we use n equals to what? In our previous example, the number of periods per year.
12.
12. Okay, so it's compounded per month, right? Now, of course, we know that it is possible that we compound the money every day. In fact, if somebody crazy enough, they will compound the money every second. Okay, so basically, what happened when this n? What happened when this n goes to infinity? Then you will see this part here gets smaller, right? However, this part here gets larger. So then we found out that when n goes to infinity, the formula now becomes continuously compounding formula. This is P e to the R t. Okay, so let's say I use the same example earlier. Let's say the initial amount is 20,000. The interest rate is 1.2%, which is 0.012. Now, suppose we compound this continuously, then what is the amount of money after 4 years? And it will be 20,000 times e to the 0.012 times 4. That's 20,000 times e to the 0.048. Now, I hope you know where to find your e. I get, I'm sorry, I get $20,983.41.
Professor, quick question. Just wondering, when would we encounter a situation where we can compound something continuously?
We have more and more cases like that. Even though I say we compound it continuously, but you will see the number, the final number that I have here, I use this example, okay? The number I get here will be very similar if we compound this every hour. Basically, if the number of periods annually becomes very, very big number, right? The number of periods annually becomes very big number. It doesn't have to be exactly infinity, you know, as long as it's big enough. As long as it is big enough, then you can already use this formula here. Of course, theoretically, they're supposed to say compounding continuously. But even if we say we compound it hourly, you will see the number is actually very close to this.
Okay.
Maybe I say it another way. You will see that if I go back to our previous question earlier, this one here. If we compound it monthly, we'll get extra $982, $982.91, right? Okay. Suppose I change this n here, the number of compounding per year, the number of periods per year. If I increase that to 24, when I increase this to 24, you will see this number will increase. You will see this number will increase. So let's say if my n is 24, let's say n now is 24, then in 4 years, the money will be 20,000 times 1 plus 0.0005 to the power of 96. Because I compounded more, then the periodical interest will be less, right? Will be half of this. I double the number of periods, therefore the periodical interest will be half, yet the number of periods will be double too. When I compute this, I know you we record this, so don't worry, you can review that again later on. So 1.0005 to the power of 96, then multiply that by 20,000. I get $20,983.16. You see that it is increasing.
Yeah.
Right? So then somebody may ask, okay, can we increase that then more instead of compounding it by monthly, like twice a month? How about if we compound it daily? Then we expect this number to be even larger. Oops, sorry. We expect this number to be even larger, right? If we compound it even more often. Now, the problem is, if we compound it even more often in 1 year for 4 years, then will this number increase to infinity? The answer is no, it will not increase to infinity. In fact, it will only, the highest you possibly get is this one. The highest you can possibly get is this. Even if you compound it infinitely many times in 1 year, this is the maximum. Okay?
Okay.
Yeah, if I increase the number of periods in a year, then the maximum we possibly get is this one. So I don't think anybody will fight for this. Like when let's say I'm the bank, and then I compound it monthly, and then you say, can you compound it every 2 weeks? I say, I don't mind, I compound it every 2 weeks. Then you get extra how many dollars? Let me tell you, you get extra 25 cents, right? Okay, and then somebody else come to me and say, you know what, Thomas, you are not fair. Why you only make it every other week? Why don't you make it every hour or every second? I say, okay, I don't mind. To get your business, I will do it. But see how much money you make. From 16 cents extra to become 41 cents. Another 25 cents.
Yeah.
Right? But you file a complaint that runs for many days. Let's say Thomas is not fair, blah, 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 blah. And then, yeah, for that you get 25 cents. So even though we have something increase n value, but it's not too much. And don't forget, this is what you get in 4 years. So you fight so hard for 25 cents in 4 years. I don't think that's worth fighting for. Now, this number becomes very different, however, if the number you put in instead of 20,000, you change it to 20 million. Then you start seeing the difference, right? That's for exponential continuously compounded interest formula. And what else in this section? Nothing more. Let me give you the suggested homework for 4.2. Suggested homework for 4.2. I would like focus on 4.2 especially. Number 1 to number 13. But for number 13, just do A, B, D, E, G, and H. Of course, continue more. Maybe, I'm sorry, not up to number 13, more. Up to number 30, let's say 30, 39. Up to number 39. But for number 13, just do part of that. You can also skip. You don't need to do number 25 and number 27. You can skip that, but the rest you can do already. Maybe on the top of that, number 45 and number 47. While for question number on 4.3, question on 4.3, I would like you to try doing number 1, and then 5 to number 9. Oh, you know what? What am I doing? Up to number 19. Yeah. Okay. Now let me go on to 4.4. I have only around 10-12 minutes remaining, so I won't be able to finish 4.4 completely, but I can give the foundation. 4.4 logarithmic function definition. For a positive and not 1. Log base A of x equals to y if and only if a to the y equals x. I need you to memorize this definition. As for the base, don't worry, that's the same base that we talked about. Okay, but how do we define logarithmic for now is we say this is the log form, logarithmic form, and this is the exponential form. Now for today, I will only teach you this part. I will do some examples. And then on Wednesday, we will do more, especially on the graphing and how to apply that into half-life, so on and so forth. Let's say, for example, we want to rewrite into logarithmic form. For example, number 2a. 3 to the 5th equals to 243. This is exponential form. So what will the log form be? The log form will be log base 3. Now this 3 here, that's the base, is a subscript, which means it's smaller and lower. Okay, log base 3 of 243 equals to 5. let's say part B. 3 to the negative 4 equals to 1 over 81. What will the log form of that equation be? It will be log base
Base 3.
log base 3 of
1 over 81.
1 over 81 equals to
Negative 4.
negative 4. That's right. How about part C? We have C to the P equals D. Then what will the log form be?
Log C,
Log base C
log base
of
D
D
equals P.
equals P. That's right. Okay, how about part F? Part F, 0.9 to the T equals to 1/2.
Log base 0.9
Log base 0.9 of
of 1/2
1/2
equals T.
equals T. Okay, now let's go backward. Suppose I have the log form. I want to write that into exponential form. For a log base 3 of 81 equals to 4. So in exponential form, that will be
3 to the 4 is
the base is
3,
3 to the power of
4,
4 equals 81.
81.
How about part C? Log base phi of W equals to Q.
Base B
Mm-hmm.
9 equals to
To the
W.
power of Q equals to W.
Yeah, Q.
Okay. Now you will see that this log function is also one-to-one function because it is actually the inverse of exponential function. Because of that, then we can use the property, the one-to-oneness, to solve some problem. Let's say, for example, number 6, 3 times a to the 4t equals to 10. How do we solve for t? Solve for t. So what I will do first, I divide by 3. Now then, when I want to get the exponent, I apply log. So I rewrite that into log form. Log base a of 10 over 3 equals to 4t.
So you have to clear the constant.
Actually not constant, but I know what you mean. The coefficient, to be more precise.
The coefficient. Yeah, yes,
Yeah.
yes.
Yeah. Okay, and then to have t by itself, then I will divide by 4 further. 1/4 log base a of 10 over 3. Okay. we have more exercise for you to do later on. Let me jump all the way to, for example, number 16. Number 16 is find the number or find the value. Number 16, G, for example, are G log base 2 of 128 equals to what? How do we solve this problem? Let's call this X first. Let's call this X first. And then I will rewrite that into exponential form. What will this be in exponential form?
Exponential form.
2 to the x equals 128.
Mm-hmm. Now then we will rewrite that 128 into 2 to some power.
To the 8
I think 2 to the 7.
to the 7.
Yeah, 2 to the 5th is 32. 2 to the 6th is 64. 2 to the 7th is 128, right?
Yeah.
Okay.
Yeah.
Now then by one-to-oneness that we learned before, x equals to 7, which means log base 2 of 128 is equal to 7. Now, how about part E? I kind of step back a little bit. How about part E? 5 to the power of log base 5 of 4 equals to what? Now, let's call this x for now. Let's call this x for now. If log base 5 of 4 is seen to be the exponent, if that's the exponent, then we can see that equation in exponential form, right? I mean, you can see that equation as exponential form and take a look now on the log form. Log base 5 of the answer equals to the exponent. You see that? It's like maybe you see 5 to the blah equals to 4 means log base 5 of 4, I'm sorry, of to the blah equals to, not 4, I'm sorry, it should be x there, equals to x, then log base 5 of x equals to blah. That's what I did here. Okay, now then, by one-to-oneness, we see that x equals to 4. My point from example G and example E here, number 16G, 16E, is when we try to compute the value, we rewrite them in exponential form or in logarithmic form first. Then it is easier to compute from there. Okay, now let me give you the suggested homework from here. Please do this suggested homework. It is on easy side. Okay, not that hard yet. The lecture video I asked you to watch already include the whole 4.4. In fact, already include 4.5. So on Wednesday, between now and Wednesday, continue watching the lecture video I asked you to watch. Okay, because that already covered up to 4.5. 4.4, the easy part that I wanted to do is from number 1 to number 19. Maybe no. Yeah, up to number 19. Up to number 19. Okay, do as much as you can. And then again, on Wednesday, I will continue from this 4.4. I believe I will go up to 4.5. And then next week, Monday, I will do 4.6. And I will start a little bit with trigonometry. So before the spring break, we will start trigonometry already. Okay, see you then on Wednesday.
Bye.
Bye-bye.
Bye. Have a good day.
You too.